Okay, welcome to section 5.5, substitution method part 2. When evaluating definite integrals, there's two methods that we're going to be able to use when we use substitution. The first one being we're going to evaluate the indefinite integral first and then use the fundamental theorem of calculus. Now, that's a way we can do it, but we don't always use it. Okay, we're going to primarily use method 2, which is changing the limits of integration when the variable is changed. And you're going to look at examples 2, 3, and 4 using this method. I'm going to show you this first and just let you know that we can use this method to evaluate definite integrals, but number 2 is preferable. So, in example 1, we're going to evaluate the integral from 0 to 4 of the square root of 2x plus 1. We did this earlier in video number 1, so this should seem repetitive. Now, we're going to go from 0 to 4 and we're going to integrate the square root of 2x plus 1 dx. Now, what that first rule says is first look at the indefinite integral of 2x plus 1, and we're going to evaluate that from 0 to 4. When we do that, remember we let u equal 2x plus 1. So du dx becomes 2, and solving for du we get 2 dx, and again we don't see 2 dx anywhere. So what we have to do is solve for dx, and we get du over 2. Okay? And when we integrate this, we have 1/3 u to the 3/2. U is 2x plus 1, so we resubstitute that back in. This 1/3, remember, comes from taking 1/2 times 2/3 u to the 3/2. And remember that when we integrate it, u to the 3/2 divided by 3/2 is the same thing as multiplying by 2/3. The 1/2 comes from that du being substituted into dx. So we take the indefinite integral and then we use the fundamental theorem of calculus to evaluate from 0 to 4. So here's your f of b minus f of a, the fundamental theorem of calculus. So 4 goes in for x, you get 8 plus 1, which is 9 to the 3/2. You plug 0 in here, we get 1 to the 3/2. So you have 1/3 times 27 minus 1, which is 26/3. So before we look at method 2, we have to look at how we define the substitution rule for definite integrals. Now, if g is a continuous function on AB and f is a continuous on the range of u equals g of x, the following occurs. Now, it's really hard to look at this and understand maybe what's going on, but you have a function inside of another one, a composition, times the derivative. So you have this g of a and g of b. So notice how we go from a lower sum and an upper sum of a and b to g of a, g of b. So what this tells you is that you're going to plug each of those values, a and b, into u. Whatever you pick for your u, you're going to plug a and b in and get two new boundaries for your area under a curve, essentially. We're going to have g of a, the lower, and g of b, the upper of f of u. So let's look at an example. Example 2 says we're going to go from 1 to 2. We're going to integrate dx over 3 minus 5x. So as before, we're going to pick u. In this case, we're going to let u equal 3 minus 5x. Taking the derivative, you get du dx. That's equal to negative 5. So we solve for du, we get negative 5 dx. And du over negative 5 is equal to dx. So when we look here, negative 5 dx, we don't see that anywhere. So solve for dx. So let's look. We look to rewrite our integral from 1 to 2 of 1 over u squared by substituting u in for 3 minus 5x. Times, instead of writing dx, we're going to write du over negative 5, which I've done here. Nothing simplifies, but I can bring that negative 1/5 out. So I do. And now if you look, all of a sudden I have a new lower and upper bound. I've gone from 1 to 2 to negative 2 to negative 7. So that's where we plug a and b into u. So here I've shown when you plug 1 in, you get 3 minus 5. which is negative 2, the lower bound. And when you have x equals 2, you plug 2 into u, and you get 3 minus 10, which is negative 7. So there's our new bounds, our lower sum and our upper sum, okay, of du over u squared. Now, when you integrate 1 over u squared, that's just negative 1 over u, and I brought the negative out front. And now I plug both negative 7 in for u and negative 2 in for u. So I have negative 1/5, okay, and I plug negative 7 in, that's negative 1/7, and negative 2 gives me a positive 1/2. Okay, and so negative 1/5 of the sum of negative 1/7 and 1/2 is 1/14. So when we look at another example of using rule number 2, switching the lower and upper sum, we're going to evaluate this integral from 1 to e of the natural log of x over x dx. So again, I pick u, and I'm picking u to be the natural log of x. That derivative is 1 over x. Solving for dx, I get x du equals dx. So let's look at the integral. 1 to e of natural log of x over x dx. I put u instead of natural log, and I get u over x times x du. So I've substituted now dx, and I've used x du, because that's what dx equals. So look, the x is simplified to be 1, and now I'm going from the integration of 1 to e of u du. Okay? I integrate u, which is u squared over 2, and now here's where I change my bounds. I've gone from 1 to e and 0 to 1. How do I do that? Well, I plug 1 and e both into what my u function is. So the natural log of 1 is 0. The natural log of e is 1. So that's how I get those new bounds. I plug a and b into u. In this they call the g of x function by the definition on slide 2. That's your g of x. So you have g of a and g of b going in. So the answer becomes 1/2 because we substitute 1 in for u and 0 in for u. Now our last example is from 0 to 2 of dx over 2x minus 3 squared. So again, same thing. I'm going to let u be 2x minus 3. I differentiate, and I get 2. Du becomes 2 dx. No 2 dx here, so I solve for dx, and I get du over 2. So you can see by simplifying the integration, 0 to 2, okay, and this is going to be 1, I erased this earlier, 1 over u squared times du over 2. Now, nothing to simplify, so I bring the 1/2 out front, and we're going to integrate from negative 3 to 1, and notice there's the switch. So I plug 0 and 2 into u, and when I plug 2 in I get 1, and when I plug 0 I get negative 3. So now I have 1 over u squared, and I'm differentiating, or anti-differentiating that, which gives me negative 1 over u. So now I have to evaluate from negative 3 to 1, and I plug both those values in to this function and simplify, and this is what I do here. I plug 1 in, I get 1/2. I plug negative 3 and I get 1/6, and the area, the evaluation becomes 2/3. Okay, so I hope that helps, and this is how we take u substitution with definite integrals, and I'll see you for the last video in this series.